Hello. Hello. Thank you for all coming along tonight to talk about the periodic table. The RI is an absolutely extraordinary place. Hands up if you've been here before. That's most people. I mean, it's a phenomenal place. I'm delighted to hear that so many of you watch Christmas lectures as well. I think here is a particularly fitting venue for a show on the periodic table. Who knows how many elements were discovered here? Got a few hands. Yeah? Oh, drawn a blank. Anyone else? How many elements? 10. 10 elements. Primarily by Humphrey Davy working in this very building and discovering elements, things that had never been seen before. And the periodic table is something that has always fascinated me and intrigued me. And the more I learn about it, the more interested I actually get. So did everyone have a glow stick? Yeah? Yeah, so that's quite a nice thing. Well, I'll explain why in a little minute. So this is what we're here to talk about tonight. Now, who thinks this looks interesting? You lie, some of you, I think. I think it looks as dull as anything. It's a grid, and it's just a box of letters and numbers, and it's not very inspiring at all. And that was my starting point. Like, my background was I was a chemical physicist, and then I turned into a chemistry and engineer for my PhD, and now I spend my days talking about my love of science to people. And this was up on my classroom wall, as many of you will remember it, and it will be in your classrooms today, and it's up there. But what's actually interesting is, if you think about it more as a kind of little housing block, or an advent calendar, and behind each one of those little doors tends to be a fascinating tale of discovery, or an interesting use, or someone famous that discovered it, used it. And so I just went about and I tried to track down some of the tales from the periodic table, some of the people involved in discovery, and I think there's some quite amazing things that I wanted to share with you. But the first thing is that I want to do is I'm looking for some volunteers as we go through tonight. So if you're keen to volunteer, I'm not even warning you what it's going to be for, but if you're keen, if you stick your hand right up high, I'm going to run around the place with some envelopes and give them out randomly as I can. Let's try and fight my way in. Now I'm going to throw. Beware of the corners. These things are lethal. So there we go. Oh, someone over here. And right, cover your eyes. Cover your eyes. Be careful. I'm going to throw it. And I never know where it's going to land. If you don't want it, just pass it along. Again, careful, careful, careful. It's like a deadly frisbee. I'll come and do some over this other side here. Again, brace yourselves. They're like boomerangs. Oh. You're brave. Whoa, nearly in the gallery. It's like the Crystal Maze. They're not getting very far. I apologize. It'd be better standing at the back and throwing them down. I promise you I'm just not that bad at throwing. There is the envelope. Oh, that was a good one. We're going to have another go. We're going to have one more go. Oh, in the face nearly. Right. Okay, so you can just keep hold of those just now, the chaos ensues. So we're going to talk about the periodic table. And the first thing that springs to mind when I think about the periodic table, as well as not myself, is this guy here, one of the famous beards of science. Does anyone know who this character might be? Yes, this is Dmitri Mendeleev, and he's credited with creating the first periodic table. So what is the periodic table? Well, it's a grouping of the chemical elements, the building blocks of everything around us. Each one is slightly unique, and Dmitri worked out how to put them in a nice little block that explains a little bit about how they behave. So the periodic table is laid out not just to look pretty. It's very, very functional. It tells us a lot about the actual elements themselves. But Dmitri is quite an interesting character himself. So yes, he discovered the periodic table in 1869, but he had an interesting history. So his dad died at quite a young age, leaving his mum to care for their 13 to 17 children. The fact that they lost count says it all, really. We're not entirely sure how many brothers and sisters he had, but that must have been an amazing breakfast table. And Dmitri, from a young age, showed some promise. Enough promise that his mother decided that he was going to be special. He was going to go to university, while the rest of the cohort went off to work in a glass factory. So the rest were sent to work in a factory as children, but the mum put him on a horse. They rode a horse together all across Russia. And they went to the university in Moscow, and they said, and she said, "Look at my son. Look at the genius that he could become. Take him and mold him into one of the finest scientific minds the world has ever seen." And they looked at him and they said no, which was a shame. So back on the horse they went. They rode to St. Petersburg, where he did get in and he did create the first periodic table. So let's just have a look again at that periodic table. What does it tell us? Well, for a start, things over at this side are a little bit smaller. So that's, if we start smaller, we get bigger as we go over here. Because what we're doing is we add in an electron. Think about it like typing on a typewriter. So you start at the left-hand side of the page, and you type all the letters. You add a letter, you add a letter, you add a letter, and eventually the line is filled up, and you kind of hit return, and you jump back to the next side. And on a new line, you start adding in the letters, adding in the letters, adding in the letters, until you have to jump down a line. And that's what we're doing in the periodic table. We're adding in not letters, but electrons. So each one you go to the right-hand side, you're adding in an electron and a proton. So they're getting a little bit bigger. Also, up at the top, not many letters or electrons and protons have been added. They're quite small, quite light. And as we work our way along the lines, adding in those protons, we're getting heavier, we're getting bigger. So again, as we go down the periodic table, we get to bigger, heavier elements as well. So I want to talk about a few of the different elements that we have. If you have an envelope, can you open the envelope up for me, please? And we'll see what's inside. So if you just kind of rip it open and hold it up so that everyone else can see, and we'll have a little look and see what everyone has. So they're starting to appear now. So if you have a little look around, you can see some elements popping up around you. Now, as we go through the talk tonight, you're going to become my elements. You're going to become the elements that you're holding on to. Some of you have lovely stories, lovely uses. Some of you, I'm sorry for that. It was luck of the draw what element you got. Some are going to be a bit horrible. But that is the glory of the periodic table. So you can put those down now, and we're going to think about our very first element. And the first element that I'm going to pick is sodium. Is there a sodium in the room? So Na, right at the front. There we go. So you can just stay there for now. You can just stay there for now while we talk about you. So we're going to describe what you are like as an element. So you are now sodium. Okay. So sodium. We can see it quite far up at the top, left-hand side there. You can see it's 1, 2, 3 down, and it's in the first row. Because it is over at the very far left-hand side, it's only had one letter, proton, electron, added in at that side. And it doesn't really want to sit like that. It's very fiery and reactive. The elements aren't happy unless they've got big full shells or lines. So they want is to kind of fill themselves up so they're nice and full, and then they're quite content. But if they only have a little bit, 1 or 2 electrons or protons added in, they don't like that. Or if they have 1 or 2 missing, then they don't like that, and they get quite reactive. So sodium over here has one little electron orbiting around the outside of it, and it wants to get rid of it. And that makes it reactive. Very, very fiery. So you're quite a violent person. You're quite fiery and reactive. Look, you're ready to go. You're ready to go. I've got a little video. I've got a little video of what would happen if we took you to the swimming pool. Okay? So can we see the video?
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
It's a firework display. They used it in the Second World War. They separated it. So it's the salt that we eat is made of sodium and it's made of chlorine. And America were taking those and separating them out. And they were using chlorine as a weapon. And they just had lots of sodium left over. And what do you do with leftover sodium? Apparently you find a lake and you throw it in. So you are fire reactive. Do you want to come forward? Because you're our sodium. You're our very first element. And we want to make sure we recognise you for the element that you are. So as a fiery, reactive little element, can you just slip this on? So a little fire outfit. If it fits, just. Also, we don't do half measures here. So we've got a hat, a small axe. I'm not sure that's going to help you. And the trousers are probably more hassle than they're worth, to be honest. But we're not going to miss you. So let's have a round of applause for our first fiery sodium element. Well done. You can just sit back down now. Thank you. Just keep that. Well, you can keep it on. I would keep it on. We don't want you bursting into flames. So that's our first element. Let's see. Hold up your cards and let's see what other elements we've got kicking around that I can maybe mention just now. Let's see. Helium. Why don't you come down? You come down for me if you would, helium. We'll jump right over to the other side now. So we're right over at helium. We're welcome helium down. We're going to talk about you. So you're over on the right-hand side. So you're, fairly dumpy. You've got a nice full shell. You've got a full line. You're not very reactive. You're a bit dull, to be honest. But we love you nonetheless. Now, helium is an element that we're quite familiar with. Where might we see helium? Yeah? Where might you see it? Inside a balloon. I've got a balloon. So we've got some actual helium here. Who loves balloons? Shame on you. Helium is a very, very precious resource. Where do you think helium comes from? Right up the back there. Where do you think it comes from? It comes from rocks and caves in America. Exactly right. We dig helium out of the ground. People think it comes from the air. It's in the air. No. We've dug this from deep inside the earth. And as this balloon deflates, the helium will escape. And because it's lighter than the air, it will carry on floating up and up and up until it will eventually leave. It'll disappear into space. So the helium that we have just now is a very finite resource. We won't have it again. And we need it for various medical and scientific applications because it is this very unique, kind of very light, but very unreactive gas. And so in 100 years' time, it will probably seem crazy that we put helium into balloons just for fun. This would be like gold-plated balloons. It's extraordinary. So actually, we shouldn't be using helium just for fun. We need to keep it and preserve it, because the helium that we have just now is going to run out, and we're not going to be able to get any more. So helium, you might be a bit bland, but you're very precious to us, and we don't want you to leave. Don't float off into space. Let's have a round of applause for helium. Thank you. You just take that with you. We might hear a little bit more from helium later. I've brought along a couple of friends with me tonight to talk about the elements that they love. Because each person thinks about elements in a different way. They think about the periodic table in a different way. And so one of my friends that's come along tonight is Suze Kundu from Imperial College. And she's fantastic. We've done loads of shows and things like that together. And she has one particular element that she wants to champion tonight. Now, unfortunately, it is the worst element out there. But she loves it nonetheless. You can make up your own mind about it. So to talk about my least favourite element, please welcome Suze Kundu.
Thank you. Hello everyone. Now, contrary to what Jamie said, I actually don't really like this element. I'll tell you why in a moment. So my element is carbon. Now, for background, I'm an inorganic material scientist, and we'll come to that in a bit, but it kind of contributes to why I don't really like carbon very much. So I like lots of other elements. It's not like I'm just grumpy and I don't like the elements. I love gold because I can wear it without reacting. I like titanium because it's strong and it's really, really light. I like hydrogen because it's tiny and it's the future. But I felt a bit bad for carbon because I'm all about the inorganic stuff that basically just doesn't include carbon. So I thought I would give it a fair go and I'd see whether I could, in fact, cheerlead it. So let's say hello to carbon. Can everybody say hello, carbon? Yeah. Quite friendly. Some scepticism over there. Impress me, carbon. Okay, all right. Well, we'll see. We'll see what carbon's got. Now, carbon, as Jamie's sort of taken you through the science behind it, it has an atomic number of 6. So it has 6 protons and it has 6 electrons. Now, its atomic mass is 12. Well, 12.01 on average. Now, that means that it has 6 protons in its nucleus, and it also has 6 neutrons. So they kind of weigh the same thing. Now, actually, carbon has a connection to all of the elements, because all the elements have this atomic mass. And the atomic mass unit is defined by carbon, by a 12-carbon atom. So 1 atomic mass unit is a 12th of a 12-carbon atom. So it does have connections to everything. Now, where is carbon on the periodic table? Well, it's over here on the periodic table of cupcakes. Because why not? My friend Toby helped me ice these for a long afternoon. Do you know what's really annoying? You make a periodic table of cupcakes, you take a photo of it, and then 2 days later somebody points out that hydrogen is upside down. Anyway, so here is carbon. Carbon is over here. I hope you can all see that big pink arrow pointing to carbon. Now, sort of diagonally towards the left of it, all of those are metals. Diagonally towards the right of it and including it, those are non-metals. So the white cupcakes, the orange cupcakes, the lilac cupcakes, these are all non-metals. Everything else aside from the brown ones are metals. Now, these middle ones are these metalloid elements, so they're kind of in between. Now, we are familiar with carbon, but we're familiar with carbon in very different forms. We have seen carbon as diamond, and we've seen carbon as graphite. Now, these are polymorphs, so they're all made of carbon atoms, but they have very different properties, these different forms of carbon. They're also known as allotropes because they're different formations and different structures using just an element, just an atom. Now, we know that these have very different properties. I'll come to those in a moment. Now, one of the reasons that I'm kind of a bit non-carbon is because I am an inorganic scientist. Now, organic chemistry is a chemistry that is associated with the chemistry of carbon-containing compounds. So, organic I feel a bit bad for carbon in that the word organic is somewhat misused. This is an organic cucumber. Cucumber? It's a carrot. It's a carrot. Find me an inorganic carrot and I will be impressed. But obviously a lot of the stuff around us, including us, we're all made of carbon-containing compounds. So carbon does have its uses. Carbon is great. We breathe it out. We're made of it. There is a whole cycle associated with carbon. It kind of recycles. It's everywhere. It connects us on the earth to the air. It's constantly going round and round in different forms and in different chemicals. So it is quite important. We have carbon footprints. And this is something we have to worry about. Now, these are the carbon-containing compounds that we release in our everyday lives as people and as organisations. So carbon is something we have to consider. So this is carbon dioxide over here, and this is methane over here. So these are things that we're producing a lot of the time through burning fossil fuels, emitting greenhouse gases a lot of the time. And these all contain carbon. Now, carbon does have some exciting uses. We can actually find out how old things are by looking at the carbon within them. Now, I did mention earlier that carbon, on average, weighs about 12 atomic mass units. Now, the average comes about because not every carbon weighs 12 exactly. There are some that have an extra neutron in them, and these are known as isotopes. So they're still carbon, and they still behave like carbon because they still have 6 protons and 6 electrons. But because they have 1 or 2 extra neutrons, they're a bit heavier. Now, it's a little bit like having a suitcase or a handbag. If you try and shove too much in there, it becomes a little bit unstable. And the nuclei of these heavier carbons can be quite unstable. And so, as an example, carbon-14 starts to kind of fall apart. It undergoes radioactive decay. Now, we know that these bits of carbon kind of occur in the same proportions. So if we look at how much of that is left over, we can actually do something known as carbon dating. So we can find out how old something is by looking at the different components of carbon that remain in that particular artifact, which is pretty exciting. So carbon does have uses, which is exciting. But where do these weird properties of carbon come from? Now, we looked at diamond, we looked at graphite, but where does it come from? Now, this is a diamond. Now, I'm a material scientist and engineer, so I'd look at the properties of this diamond. Now, this diamond, I would say it's translucent. It's one of the toughest materials known to man and woman. I'd say mostly woman. That's a very cute giggle. It doesn't conduct electricity. And these properties come about because of the way that these carbons are arranged. So I'm just going to run and fetch my massive diamond. Here it is. I did not pick this up next door from Tiffany. I picked this up from the Royal Institution. Now, this is diamond. Now, in diamond, you can see that the carbons are arranged in a very sort of 3D, very rigid structure. If we focus on one carbon in particular, you can see that it's joined to 4 other carbons. It's creating a very rigid structure. Now, carbons don't have to be arranged this way. They can be arranged differently. They can be arranged in these layers. Now, a layer like this, I must apologise because these don't match. This is an example of what graphite would look like. Now, this is just a layer of graphite, and each carbon is joined to 3 other carbons. So it creates these flat layers, and these layers can brush past one another. And this gives rise to a much softer form of carbon, this graphite here. Now, it's the same atoms that we're looking at, but because of their arrangements, they have very different properties. Now, carbon in a graphite form can actually conduct electricity. So carbon, depending on how you arrange those atoms, lots and lots of different properties. But it can get even cooler because we can actually isolate just one of these layers. And we get something pretty amazing. Now, it's one of my favourite materials. Just a single layer, one atom-thick layer of carbon in its graphite form is known as graphene. And graphene has some amazing properties. It's really light, it's really flexible, It's super strong. If you can get some graphene, layer it up a little bit to about the thickness of cling film, that is strong enough to support the weight of an elephant. Now, I was lucky enough to do this experiment on this very stage a while back, just to prove that that is indeed the case. Yeah, that's Princess Fluffles up there, making her Royal Institution debut a while back. She really enjoyed that. She really milked it. Yeah. But you can get some other properties from this graphene as well. It's great at conducting not just electricity along this plane, but it's great at conducting heat along this plane. And it doesn't really lose it either. So I have got a chunk of it. Now, obviously, if something is only an atom thick, it's quite difficult to handle. But like I said, you can layer it up, you can laminate it, and you can get this stuff. This is known as pyrolytic graphite, which is graphene kind of layered up. So it's easier to use. It's easier to handle, but it maintains a lot of the properties of graphene. Now, it's so good at conducting electricity that I can hold this ice cube here very gently. I'm not even pressing it. Just hold it onto the ice. Now, it's conducting the heat from my fingertips straight to the edge of this piece of ice, to this piece of graphene. So much so that it's just cut straight through. It's like a hot knife through butter. You don't even put pressure on it. It's the weirdest feeling in the world. Now, what's the point of it, aside from, I don't know, creating some beautiful ice structures, perhaps? Well, you can do a lot more with it. Now, I will come to the uses of that in a moment. But what I'm going to do is manipulate my graphene. I'm going to create something even cooler. I'm going to attach these together to form a different kind of carbon structure. Now, these are all nanostructures, and that's because these are nanodimensional in one of their 3 dimensions. So this is a carbon nanotube. Now, you've probably heard of these. You've probably actually seen them and used them. They're used to reinforce tyres and things. They're very light, but again, they're very, very strong. And they can be woven into fibres, so you can create carbon fibre as well. Now, it's retaining a lot of the properties of that graphene. It's strong, it's light, and it's flexible. Now, it'd be great to use something like diamond, but diamond you can't really manipulate, and it's incredibly expensive. So you can use this stuff for reinforcement, or you can do something even cooler with them. You can start to cap the bottom of these, so you get teeny, tiny test tubes. You can start to do chemistry on the nano scale, just using carbon that's everywhere. You can even start to wrap them around each other even more to create these cage-like structures. This is known as a buckyball. It's arranged like a football, so it's full of hexagons and pentagons. Now, what's the point of a nano football, you're probably wondering? Is it just so that the nanobots can have their Champions League match? Well, no, although they might want to. You can actually start to put chemicals inside these and deliver them around the body by attaching little markers, little signposts, so that they know when they've arrived at their destination. Targeted drug delivery can be achieved through things like this. So even though I'm a little bit mean about carbon, I must admit it does have some pretty cool uses. Not just in the everyday, where we've got diamonds on drill bits, where we need to use that really tough property of theirs to drill through stuff. We can actually start looking way beyond our homes, in fact, way beyond our planet, using things like carbon nanotubes and graphene, things that are really light but really strong. We can start to head into space. Now, I know you're thinking, we already go into space. We use rockets for that. Well, for every kilogram that we send up into space, that costs us about $20,000. So if we can find a cheaper way of getting into space, that would be pretty cool, because we can do it a lot more. So why don't we just get the lift? Now, building a lift out of the stuff that we usually make lifts out of could be pretty tricky because steel is really heavy. You're going to have some problems there. But we can start using things like carbon nanotubes and graphene to actually get us up into space to a geostationary satellite. So this is why I think, despite the fact that I have been a little bit mean and a little bit dismissive about carbon, I think it's in our past. It's very much in our present, and I think it could take us into the future. Carbon, where are you? Are you here? Can you wave at me? You're over there. I would like to award you with the buckyball. Would you like to hold onto the buckyball as a token of you being just amazing and vital to life? I would kick it to you, but I don't want to. This is for you. I think a big round of applause for carbon generally. Thank you. You can head up to your seat. And thank you guys very much for letting me attempt to cheerlead something that I have just completely ignored for quite a long time. Thank you very much.
Thank you. I was really mean about carbon. I am a bit convinced. I mean, there's some amazing things. I mean, these structures, you know, the same atom, but used in very, 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 very different ways, is something quite extraordinary. So I am softening a little bit to carbon. While we're on carbon, let's look at something similar. So Suze took us through where carbon was on the periodic table, so we can see it up there. And I talked a little bit about going from side to side and how the properties change, fiery and reactive, to a little bit more calm at the other side. But I didn't really talk about going down. So as we go down, if you take one of those columns, the atoms behave in a similar way. So if you look at carbon, it's at the very top of one of the little columns. If you go down just one, then we'll find silicon. Where's my silicon? Silicon. So what we know about you is you behave in similar ways to carbon. You want to form the same amount of bonds, and that's why Suze explained, you know, we are carbon-based life forms. Carbon is really essential to make us living, breathing creatures. But if you're a fan of sci-fi, you might have heard of silicon-based life forms. And that comes from the trends in the periodic table. We can see that if we're carbon-based, then we want something that would behave in a similar way to carbon, and so maybe we could have silicon, because we know it would behave in a similar way. And that's why the idea of silicon-based life forms came from. But we don't have silicon-based life forms with us tonight. We have more earthbound uses of silicon. So we might associate it with something like sand or glass is made out of silicon. Silicon, do you want to come forward? I have some actual silicon for you if you come down. So another use that we find, oven mitts. Sometimes silicon is used to kind of protect us from high temperature. So these are our silicon pads. But also, in this frame here, if you have a little look in there, that's just kind of a mirror, isn't it? And it's actually one of the best mirrors you'll ever find because it is very, very pure silicon. And silicon is the element that we've actually managed to purify to the greatest extent. So that wafer there contains very few atoms of anything else other than silicon. And so we use silicon microchips in our computers and our PCs and things like that. And inside those, it's very, very, very pure silicon for a lot of them. So what you have there is some very pure silicon and then some kind of silicon with oxygen mixed in about it. So silicon, we use you as glass, we use you to protect us from hot things, but also we use you in all forms of electronics. And maybe, who knows, there are life forms out there based just on you. Let's have a round of applause for silicon. Thank you. So, at the start, as you came in, I gave you all glow sticks, and I want to turn to those now. So if you haven't already, I think most have, if you break them inside, don't break them too energetically. We don't want them bursting and going all over the place, but shake them, give them a little wave, and can we have the lights down as low as they possibly can go to have a little look around? That's a lovely sight. That's really, and have a little look around. Now, what you can see as you look around is you're glowing different colours. Some of you are blue, some of you are purple, some green, some yellow. And this, for me, from where I'm standing, is kind of like what it is like looking out into space. Standing on Earth, looking into space. We can have the lights back on, and you can stop your frantic waving now. Because as we look into space, we look for different colours. And you don't have different elements inside these sticks, you have different compounds, but out in space, suns are burning and giving off very distinct colours. And by looking at the colours that they give off, we can tell what elements are inside them. So most of the elements in the periodic table come from stars. stars that burn energy. They start off burning hydrogen. Then they run out of hydrogen and they use helium. And they get heavier and heavier and heavier until the heavy elements are made, right up to iron. They're made inside suns. And as we're heating those up, as we're burning those elements, they're giving off very distinctive colours. So in the way that I could look out into you and say, you have a green one and know what compound is inside. You have a blue one. I know what is burning inside you. We can look at the stars in the sky, even from far away, and look at the very precise colours that are given off, and that will tell us what element we're looking at and what element that sun is burning. Another area that you might be familiar with it in, coming back to our sodium, is street lights. So you might have seen the orange glow of street lamps, and that's because they're sodium-based. So many of the elements have very distinctive colours, and that's what I want to talk about now. I'm going to rattle through a few of you at one go, because in the periodic table, we're going to stick, we had helium, which tops this column right at the right-hand side, called the noble gases. And these are gases that we very strongly associate with colours as well. If I had to show you this, what element do we think is inside this? Yeah, at the back. Neon? Yeah. Any other guesses? Argon? Yeah, that's a good idea. So this is a neon sign. We call these neon signs. But the interesting thing is, if it's glowing blue, it's not neon. It's another element. So this one possibly could be argon. Let's identify our noble gases scattered around the room. So helium, can you, in fact, we'll just bring you down. So helium, can you come back down for us? And if we go down one, we come to neon. Where's our neon? Where are you? Neon, do you want to come down as well? Argon, where's argon? Do we have an AR? Yes, argon. Krypton, whereabouts are you? Krypton. Krypton, you come down as well. Down one, we're at XE, a xenon. Do we have a xenon in the room? Where's our xenon? XE. Oh, when you come down, and I think we've got a radon as well. RN. Is there an RN? You're a bit dangerous, so you stay over that side. So let's line you up in order. So let's helium, can you top the group here? We'll have you here. Then we'll have neon. Where's our neon? So you go next. Argon. Then we've got krypton. And then xenon. Oh, you're sharing it. How lovely. And then radon finally at the end. I said, a little bit dangerous. And we associate different colours with these. So, for example, let's see. What have we got? We've got kind of red. Radon, sometimes seen as green, sometimes as red, but radon, if we'd pass the electricity through you, if we'd kind of zap you with a high volt, you'd glow red. What else? Argon. Argon, you would be slightly blue. So where are you? Argon. Again, can we have the lights down again as well? These hopefully should light up for us. Orange, you're out here. So neon is actually orange. So if you see a neon sign that's glowing orange, then chances are it is neon. If it's glowing blue, it could be argon. If it's white, then it could be krypton. Where's krypton? So krypton, the other place we use krypton, in energy-saving light bulbs. Sometimes in cars, the higher models of cars might have a slight lilac tinge to them, and that's because xenon, passing electricity through that, glows kind of purple. And helium, I've missed you out, sorry. We use you light and floaty, but also if we had to electrocute you on the spot there, you would glow kind of pink. So can we have the lights off to see if we can see the colours? Hopefully they're glowing. Hopefully they're glowing with their respective colours. A little bit. There's a little bit there. So when you look at a neon sign, don't think of it as a neon sign. Think of it as a noble gas sign. And see if you can work out which element is inside that gas tube being electrocuted to glow that certain colour. So can we have a round of applause for all our noble gases? Thank you. And you can take those back to your seats now. So that's different ways of identifying different elements. Another element that has a very distinctive colour associated with it is potassium as well. So potassium is what we're going to come back to next. But I want to introduce another of a great friend of mine who some of you might have seen her here before. She's performed many times. She is a geek songstress. She's that's a rare breed, unfortunately. But we have Helen Arney, who's here as she's part of the Festival of the Spoken Nerd. Some of you might have heard about that as well. She's a physicist. She sings. She plays many instruments, and she's quite short. In fact, my favourite memory of Helen Arney, I've not warned her about this, my favourite memory is she was staying with me once, and I was woken to the sound of a Rosa Klebb, the Bond villain, song being written on the ukulele, which is a very extraordinary way to wake up. So we're in for a treat. So please welcome to the stage Helen Arney.
Here to represent a particular element that I'm a huge fan of. But before we do that, I should probably address my dress. Some of you saw me wearing it as I was walking in. Yes, this is a dress made of the entire periodic table. When I'm wearing this, I am literally in my element. So if you enjoyed that pun, I've got plenty more of them, don't worry. I was going to do loads of them, but to be honest, the best ones are gone already. Jamie's done a few of them already. Anyone asking about the material? It's jersey, which means it's completely non-iron, apart from this little section here of atomic number 26. So if you all know about that, don't ask where my noble gases are, though. That's the only thing I request if you want to know about this dress. So I love the periodic table. I'm a physicist, but I love the poetry of the periodic table. This image doesn't do it justice. When you speak the words of the periodic table and you mix them together in compounds, it's incredible. You have technetium, titanium, tellurium. They all roll so beautifully off your tungsten. And it's the kind of thing that you want to make poetry about. And I love writing songs about science. And I was asked by the Royal Institution to write a song about an element. And I chose not one of the popular elements, not one of the fun elements, not one of the elements that everyone knows about. I chose the one that needed the biggest makeover. It's an element that most people don't notice on the periodic table. If it wasn't there, you probably wouldn't be sad. It's got the kind of name that doesn't sound very inspiring, but it was one of the elements discovered here at the Royal Institution. So what I've done is I've written a song to give it a kind of popularity boost and let people know what it's useful for and that you shouldn't judge an element just by its name. Because this is an element that's used for so many different things. It's an element that gives fireworks their green colour. It's an element that you use to make Pyrex bowls. This is the element you use to create insect repellents. You use it to make semiconductors and you mix it with silicon to make all the extraordinary things that happen in your phone. This element, however, has the dullest name on the planet. Some of you might have guessed which one it is already. We're talking about boron. So this is a song that I hope will make you feel a little bit more positively about boron. If you want to make a super hard glass or a ceramic, you need boron. And if you want to kill an insect but not harm a mammal, you need boron. And if your nuclear reactor gets carried away, Captain Boron will save the day. You should have found a different name for the element boron. All right, second verse. You know what to do when I pause, and I want it nice and loud. Okay. So you want to make a super duper semiconductor. What do you need? You need boron. So you want to make an amazing semiconductor. What do you need? Yeah. And if Humphrey Davy found you again, maybe he would name you Interesting M. They should have found a different name. They should have found a different name. They should have found a different name for the element boron. Boron's the winner tonight. Thank you very much, ladies and gentlemen. Can we keep that round of applause for the wonderful Jamie Gallagher, who is going to come and help me find boron.
Where's boron?
Now, don't be shy. You've got a whole song written about
you're
you now.
Brilliant.
Yes.
Boron.
Is that it? That's it? Perfect.
Come down, fight your way down.
So this is my favourite use of boron. Is in the song I called it Captain Boron, because it's used to absorb extra neutrons in a nuclear reactor so that it doesn't go horribly wrong. So you are a lifesaver. You are Captain Boron. And therefore, ladies and gentlemen, Captain Boron. Thank you very much. We'll see you at the end.
Helen Arney, everyone. Brilliant. I love the fact, like, even Helen, we were talking about doing this, and she said, like, oh, well, there's one element I wanted to talk about. I want to talk about boron. She's like, are you already speaking about it? No, it's fine. It's yours if you want it. But boron, absolutely wonderful. So I said I would come back and I would talk a bit about potassium. Where's potassium? Potassium. Okay. Hello. You have a very distinctive colour. Do you know what your colour is? Anyone know what colour might be associated with potassium? Even have a guess?
Blue.
No, it's not blue. If we set fire to it, we might get a...
Green.
Not green.
Red. Red and orange.
Red and orange. Not quite. Very close.
Yellow.
Yellow. You were close with red.
Yellow.
Someone said it. So not purple, not red. Who said lilac? Spot on. That's the way it's normally described. Let's see if we can see some lilac flames of potassium. So I've got a compound here. This little powder is black just now. It's kind of dull. Nothing much is happening with it. But it has some potassium in it. Now, is potassium, can anyone see it? It's K. Can you see it? Can you spot it on the table? Yeah? Is it dull and boring? Fiery and reactive? Yes, it's fiery and reactive. So, I'm going to put some see, I've got to call it boron now. I want every element to be boron. I've got some of this. So this is called potassium permanganate, and I'm going to tip it out there. Okay, so it's just a black powder. It's not doing anything very exciting or dramatic at all. But I'm going to mix it. I've got some oil here, so it's carbon-based. We heard about carbon earlier. And I'm going to mix the two of them together. And hopefully, they'll have a little bit of a fight together. And we'll get a little bit of flame. And what will happen is the potassium will start to burn. And hopefully, give off a very distinctive colour. So I'm just going to add this in here. And could we have the lights down as well? It might take a little minute just to get going. I'll put this screen up just in case anything goes terribly wrong, in which case only I will be engulfed in flames. It's like a lit firework. This is a science experiment. We never know if it's going to work. There's some smoke coming. Let's look. Can we get a lilac flame? Look for a little pink glow. Yes. Now, you might also see, do you see a little kind of flash of blue and a little bit of orangey yellow as well? That's not the potassium, that's the carbon as well. So we associate normal flames. Most of the stuff that we burn is carbon, and that gives us the kind of yellowy glow. But at the start there, there's a little flash of lilac-y pink, and that is potassium's unique coloration when we burn it, giving off a very specific shade of lilac. So potassium, do you want to come forward? I'm not going to set fire to you, I promise. Now, potassium is actually pretty essential for us. It helps us in our body to communicate. Our nerves need potassium ions to communicate. And we do have a food that is associated with potassium. You might have heard that we should eat bananas, because bananas are indeed potassium rich, and that will help your nerves communicate with each other. So a round of applause for very useful and beautiful potassium. Right, let's rattle through some more elements. Magnesium. Let's have you. Do you want to come forward, magnesium? I hope you're not feeling bashful. Because magnesium is another one that has a distinctive colour. Anyone guess the colour of magnesium? Maybe I shouldn't use the word colour. Yes, white. So let's see. So these contain some magnesium, some contain aluminium, and hopefully, do you want to hold the sparkler or shall I?
I'll hold it.
You'll hold it? That okay?
Okay.
So just don't stab anyone with it. Let's see, oh. Turn the lighter on. So we're burning carbon, so we get a yellow flame, and let's see if we light it. See it, the white? And that's magnesium. And the reason that sparklers can be a little bit dangerous is once magnesium is lit on fire, it's very difficult to put out. So it keeps burning. That's why we have buckets of sand and things to put any rogue sparklers in. Because once the magnesium is burning, it just carries on going. It burns with a very hot flame, but you're seeing that distinctive white colour. So I feel bad for you, magnesium, as well, because you're the only person that I bring up and then just burn your prop. So that's a bit of a shame. I'll give you the packet to hold. Don't start a little bonfire party back up there. But I'll take that off you. So magnesium, again, you're very fun for fireworks night, but we need to be careful of you, because if we set a match to you, we're not going to be able to put you out. So let's have a round of applause for white magnesium. Okay, who else do we have? Cards up. Let me see. Argon. We've done argon. We've had aluminium, tungsten. Oh, tungsten. Yes, tungsten. And can we do you with someone else? Is there a molybdenum? Yeah. Can you come forward? Because I want to talk about elements of war now. Actually. And what we're going to do is, let's go back to our periodic table, and we'll find both of you. So molybdenum and tungsten, let's look in the periodic table. If we look around about the middle, slightly over to the left, can you see yourselves? So in the middle. And we've got molybdenum. Now, so if you want, so come forward, tungsten. These have interesting uses. They're in the middle, and they were discovered that by adding them into steel, they could make steel stronger. So it started with molybdenum. Even as far back as World War I, they discovered that putting in some molybdenum made tanks stronger. And the Germans were able to use molybdenum to make the most advanced weapons of the day, Big Bertha, which could bomb Paris from over 75 miles away. So molybdenum, you're our first weapon of war. You were making exceptionally good weapons. But we know that if we look to our periodic table and we find tungsten, you're just underneath molybdenum. So tungsten behaves in a similar way to molybdenum. So you behave in a similar way to the thing that makes a better weapon. But tungsten is underneath molybdenum. Does that mean that tungsten is bigger or smaller? Yes. You are big and tough, and you could take molybdenum if you fought molybdenum. So, come World War II, they used the trends in the periodic table to say, well, if molybdenum is good to add into metal to make it stronger, then perhaps if we use a denser, heavier, bigger element, like tungsten, we could make a better weapon. So in a fight between tungsten and molybdenum, I know who would win. Let's have a round of applause for tungsten and molybdenum. I feel sorry, antimony, you caught my eye. I am sorry. I did say that some of the elements weren't as pleasant. Do you want to come forward? Poor antimony. So antimony is found in what we call poisoner's corner, down in the bottom right hand of the table. Now, antimony, if we ate some of you, if we took a bite out of you, well, we'd need this. Because antimony makes you need that. A lot of that. Antimony is known as the never-ending laxative, or the family laxative. And for a very good reason. You eat a pill of antimony, it does its work. You then reclaim the pill, and someone else uses it. And it's called the family laxative because it would be passed down through the generations, father to son, passed down. So antimony, I am sorry, you're rather horrible, and no one will take a bite out of you. Let's have a round of applause for antimony. What other elements do we have? We've got gold. Yeah, let's have gold. Let's have lovely gold down. Let's find something for you, gold. You're an interesting one. You've been around for a long time. People discovered you because pretty much we just dig you out the ground as you are. You're just ready to go in your pure form. So we have that's some gold there. And we can dig it out the ground just as a shiny metal, which is actually quite rare because a lot of our elements are very reactive, and so they pair up with other things to form compounds. But gold, very precious. Well, it doesn't quite fit. Let's see if the crown does any better. Something like that. Yes. I don't want to pull your ear off. There we go. Perfect. Now, gold's an interesting one because if we decided we don't want gold to be a symbol of thousands of pounds thrown away, let's say we decided we don't want gold anymore. We want another element to be our standard of wealth, to be our beautiful, pristine, precious metal. So let's decide we don't like you anymore, okay? We'll take let's work through it. Yeah, we'll give you a chance. We'll fight your battle for you. Let's start again with the whole periodic table. And let's say, right, we're going to have something other than gold. We don't want it. What's our standard of wealth be? Well, if we think about gold, we don't want a gas. We'll get rid of the noble gases. We love you, noble gases, but we don't want you because they're no good as money. They're no good to carry around in your pocket. We'll cut off the radioactive ones at the bottom because we don't want our money, our standard of wealth, burning a hole in our leg. Yeah, you can put it down. Yes, it's making a bit of a mess. Sorry. Now, we want to get rid of the fiery reactive elements at the side. We know what happens if we get sodium wet. I'm from Scotland. I don't want coins that will go off like that. We can also cut off anything that is too common or too rare. So we had silicon earlier. Silicon litters the beaches. If we decided that was our standard of wealth, everyone would be millionaires and it would all be a bit chaotic. Or if we decided something was incredibly rare, then no one would have enough. So it would be useless as a standard of wealth. So we're back to just a few small elements. And again, limiting off things that would react or would be too common or too rare. Starting with the entire periodic table, we come back to gold. So that's one of the things we got right from thousands of years, that gold is actually a perfect way to measure our wealth. It's just rare enough, but just common enough to be very precious and unreactive. So dug out the ground in a precious, shiny nugget. Let's have a round of applause for gold. Now, so there's some gold there. That's how you would dig it out of the ground. And that brings us on to our next story, which one day in Australia, in the 1800s, a gold nugget was discovered out in the outback. A very large gold nugget, which in those days would cause a gold rush. People would flock to the area that had been discovered, and they would start panning for gold, start digging, searching for other gold nuggets. And despite one huge nugget being found, they couldn't find any more, which was odd. But in the time that they were looking for it, an entire village sprung up. They built houses, they built pubs, they built shops, because that was kind of the order of importance that they went in those days. But no one could find any more gold. They found lots of these rocks here. Not precious, just standard rocks. Until one day, they were sitting around a campfire, and someone noticed something glistening in one of the rocks that was sitting around the campfire. And it was leaking gold. There was gold in the rocks. The gold was disguised because the gold had reacted with one of my favourite elements, tellurium. Where's tellurium? Tellurium. Do you want to make your way down as we tell? So what happened was, these people in the 1800s had been building their houses, their shops and their pubs out of golden bricks. And it was because the gold had reacted with tellurium. Tellurium had disguised it to look like a normal rock. Because tellurium, you're one of the few elements that will quite happily react and kind of fight with gold over there and disguise it. So as quickly as the houses sprung up, they were torn down, and everyone searched for gold locked inside. Now, tellurium, you are one of my favourite elements for many, many, many reasons. I spent many years working on you, and you have a very interesting effect. Because if I touch you, or if I had to breathe the air near you, I would smell incredibly strongly of garlic. One of two elements that induces a garlic-like odour as they process it. I've had tellurium poisoning 3 times in my life because I worked on it for many years. The first stage, you smell of garlic. Second stage, you get black nails. And third stage, you die. I only ever got to stage 1, though. The other interesting thing is tellurium was discovered in Romania, or as it was known at the time, Transylvania. And I think there has to be a fantastic vampire tellurium story. The only element to be discovered in Romania that, if you touch it, will make you reek of garlic. So tellurium, you're one of the most interesting, extraordinary, but smelly elements around. Let's have a round of applause for tellurium. Okay, we're going to have to quickly rattle through some more of the elements. This is a periodic table that I made where I looked at where the elements had been discovered, which is a very interesting thing. And it has prompted international hate mail towards me, which is absolutely extraordinary. Some of these were very difficult decisions to make. Going back into the 1700s, it's difficult to decide who discovered what element. And so some I did have to give joint credit for. And there is one there that I receive more hate mail, more vicious hate mail, for than any other element. And it's here in this room tonight. Where is polonium? Polonium. You have caused me quite a lot of hassle. Come on down, polonium. Because polonium, named after Poland, the only element to be named after a political movement, named after the independence for Poland by Marie Curie, was discovered in France. France gets the credit. She called it polonium. She loved Poland, but she was working for the University of Paris. So I have no choice but to say that you were discovered in France. But secretly, you're Polish. Round of applause for polonium. Polonium, one of my favourites as well, because Marie Curie, if most of you will have heard of her, but she was the most extraordinary person. I urge you, I beg you to learn more about the life of Marie Curie, an absolutely phenomenal, extraordinary woman. One, she discovered 2 elements, polonium and also the t-shirt that I'm wearing, which is radium, another fantastic element that glows in the dark. It was used to paint dials on World War II fighter jets that were then abandoned off the coast of Scotland, and Scotland now having the only radioactive beach in the UK because of the radium paint. Radium was seen as a miracle cure when it was discovered by Marie Curie. It was used in toothpastes, it was used in tonics. People would bathe in it as this miracle cure. It really, really didn't help anything. It gave you cancer and you died. They would use it as toothpaste, your teeth would fall out. They used it as a hair restorer, your hair would fall out. It was not a healthy element. Now, we're running vastly out of time. Let's have a couple more elements that I will rattle through before we finish up. Aluminium, arsenic, hydrogen, right, I'm going to run around. Iron. We need you to survive. Iron is found in many foodstuffs. What do we think? Cornflakes contain iron, yes or no? Yes. Iron brew contains iron, yes or no? Yes. Oh, we're not sure about this one. It does. There is iron in iron brew. It's not going to do you much good. Where was iron? Where was iron? There you are. So there's some in there. Who else do we have? Aluminium. Where were you? Where were you? We think of this as tin foil. It's actually aluminium foil. Back in the 1800s, aluminium was a precious metal, more precious than gold. And Napoleon III got cutlery made out of aluminium. He had a rattle made for his baby out of aluminium to show off his lavish wealth. So if you could just kind of form some sort of Napoleonic hat out of that. And a couple more. There's a couple that we've not managed to mention. If you want to know the story behind your element, then come and see me at the end. But I just want to finish with one last tale before Helen Arney is going to join us for one last time. But you've been such a lovely audience. I thought I'd treat you to some sweets. Now, you're not allowed to eat in here. I'm saying that now. You're not allowed to eat. But I'm giving you wrapped sweets that you're going to carry out very orderly. They're mint humbugs, so do beware. They rain down like a hail of shrapnel. They're worse than the envelopes. But I'm just going to throw some of these out. And as I do, in the 1800s, there was a sweet maker known as Humbug Billy. He sent his assistant out to buy some sugar one day. The shopkeeper was very busy and said, oh, the sugar's over there. And they made the sweets out of the sugar. It was not a bag of sugar. It was a bag of arsenic salt. Humbug Billy tried the humbugs and he felt a bit ill, but he thought it'll be fine. It wasn't. Over 200 people were poisoned by arsenic. Arsenic, do you want to come down? Where are you, arsenic? Over 200 people were poisoned. I think just under 20 people died from consuming toxic arsenic. And this instance was one that led to us having pharmacological standards. So because of your deadly kind of poisonous nature, we started taking elements and chemistry more seriously so that people couldn't accidentally make their humbugs out of arsenic salt instead of sugar. Now, what I'd like to do is, can every one of our elements come down and join us one last time down here on stage? So if you have one of the element symbols, come on down and join us. And just if you gather in a kind of semicircle around the desk there. Because here we have our living periodic table. So we've gone through from our fiery, reactive elements. Suze told us all about wonderful, complex carbon in the many different forms it could take. We had precious gold, we had poisonic arsenic, we had slightly disgusting antimony, and many, many more. Now, sadly, we haven't been able to talk about all the elements. And I can't even rattle through at Scottish speed enough elements for me to be happy. But Helen Arney wanted to come back to just mention just one or two elements more, maybe? One or two elements more. So let's welcome back Helen Arney for our last couple of elements.
Thank you. I'm just going to grab this from behind you. So some of you might know this last song already. It was created by a Harvard maths professor who set all 106 elements of the periodic table to a tune by Gilbert and Sullivan. And I have actually been spending the last 6 months learning this song. It's incredibly difficult to learn. 106 elements of the periodic table. All of you times 3, okay? And I've had to forget certain bits of information that I used to know in order to learn this for you tonight. For instance, I can no longer remember my phone number, where my parents live, or what my boyfriend looks like. All of these things are now forgotten, but for you tonight, I will perform, with your help, all of you, the Elements song. Now, something I would love you to do is sing, no, not sing, shout or cheer, clap, applaud when you hear your favourite element. So you all know what your favourite element is because you've been given it. If anyone needs a favourite element because you haven't been convinced by any single one tonight, I would suggest sodium. You know, just because it was the first one we saw tonight. When you hear sodium, clear chap, not clear or chap, clap or cheer, that's the right way around. Clap, cheer, take me around the room on your shoulders, throw a party, pop a balloon, do everything you can, go crazy. Yeah, brilliant, good, you're on. I should mention sodium's the last element of the song, so I've basically given myself a standing ovation there, so just so you know. All right, so you're ready, you're going to cheer on your favourite element? And we will see how we do, okay? Oh, this is quite hard. I'm going to psych myself up. Are you ready? Am I getting some support from you? Okay, we're ready. Okay. La 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 la. Okay, I should just mention it. I'm not just singing lanthanum, 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 lanthanum. That's not how I'm getting through 106 them. Okay, here we go. Oh, here we go. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium. I've run out of breath. Someone help me. Where's some oxygen? And iodine, and thorium, and thulium, and thallium. La 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 la. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. La 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 la. Okay, we're doing well, halfway through. How many of you have had yours already? How many of you can't tell I was going too fast? Okay, no problem, no problem. By the way, I did this song at an NHS gastroenterology department dinner. And when I said barium, biggest cheer of my career. Unbelievable. All right, here we go. We're going to do this a little bit faster. A little bit faster, Jamie? A little bit faster? Okay, right, let's step this up. We're running out of time. Martin's giving me the eye. Here we go. Okay. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium. I need a breath again, sorry. And cadmium and calcium and chromium and curium. La 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 la. Okay, let's start slow and build it up. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, zinc, and zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. La 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 la. Ah la la. Oh wow! How unexpected! Okay, no, whoa. There is something I should add, because some of you may have realized my numbers are a little bit wrong. Anyone who is a good scientist should know that if you discover that something you thought was true is actually wrong, you should change your hypothesis. You should add an appendix to your theory. So I've had to do that because 13 more elements have been discovered since that song was finished. So I'd like to add those elements which since then were discovered. But it took so long to learn this song, I really can't be bothered. La 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 la. Wonderful work. Excellent stuff. Thank you very much. I'll hand you back to Jamie.
That was brilliant. So we have at least mentioned almost all the elements, apart from a couple of very, very rare and reactive ones at the very end. I've had an absolutely fantastic time. I hope that each of one of you goes home and explores more of the history of your element. Pick your own favourite element. Pick any one. Find the most interesting story behind it. If you have something, I would love to swap it for a periodic table. So if you dump your stuff down here, I'm going to give you all a periodic table from the Royal Society of Chemistry. And I want to thank you all for coming. We had Suze Kundu with her carbon, huge cheer, and Helen Arney with every single element. Thank you very much.